Hello and welcome to Logistic Regression, explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video we are going to talk about logistic regression. In particular, we will talk about what is classification, what is logistic function due to which it is called logistic regression, and what is cross entropy loss function, which is used particularly in logistic regression. We will also see that the whole model is no longer closed form. By not closed form means it's not easy to actually come up with the parameters of the model directly. So we have to apply some iterative algorithm, and so we will be discussing gradient descent in that regard. And finally, we will do some hands-on practice in Python. If you're new to AI Sciences, at AI Sciences we actually work a lot in artificial intelligence, data science, online courses, consultancies, and all that stuff. So if you're new, please subscribe our channel and also see the courses and extra stuff all related to whatever you need. Below are the links that might be very, very helpful for you. So let's start. First of all, let me discuss what do we mean by classification. A classification problem can be posed in a following way. Let's say you have some object. Let me call this as object as x1, this object as x2, this object as x3, and each object has some label. Let's say this is the label, this is the label, this is the label, for example. And the goal for classification is to come up with a model, come up with a algorithm or software that, given the object, it predicts its label. So what happens is, in start, we have all these objects, a lot of these objects available along with their true labels. So x1, x2, the label is y2, and we can have several of these objects available along with their labels. And our goal is to use this particular data, which is sometimes known as training data. And using this training data, we have to come up with our classification model. So in particular, we have to come up with some model f, some function f, which may have its own parameters, that whenever takes some object x, it returns its label y. And at least for training data, our requirement is that for the object, the true label should be returned. There are a lot of details here, how to fit a particular model for classification. And for that, I will recommend to go through our course at AI Sciences, which is Introduction to Machine Learning in Python, which explains all these kind of things in much more detail. So briefly, we have to come up with a function, a model, which may have some parameters that finally should accept an object, and it should predict its label. And the representation of these objects are normally in the vector form. So this x1 may be vector of some numbers, 22, 41, and maybe several of these numbers, and these numbers are called features. And this, for example, in this particular case, an image contains a lot of numbers called their intensities, and we can just flatten out all the intensities into one long thin vector called the feature vector representing that image. Although there are very sophisticated feature vectors that one can compute, but at the end of the day, each object is represented by a feature vector, and the labels, they are represented by either numbers or strings or whatever. I mean, depending upon the categories, how you assign those categories. And using this training data, you have to come up with a model that eventually predicts the true labels. And this kind of scheme is known as classification. So the real question really is, what should be this FW? As we saw in our previous case, what should be this FW? Here I'm discussing all that with respect to classification, but that is also the question in case of regression and other model learning paradigms as well. One funny thing about logistic regression is, although its name looks like regression, but it's used in classification. So whenever you use logistic regression, you are actually doing classification at the end of the day. So be careful about that. So what should be this FW? Our goal is that if FW at xi, it produces some value, some prediction, let's say yi. Let me denote that yi as yi hat, that is the predicted value. Our goal is that this yi hat should be very, very close, or ideally should be equal to whatever it should actually predict. This is called ground truth, and this is what our model has predicted. In most of the cases, the prediction goes in a probabilistic way. For example, consider two classes where each yi actually belongs to just 0 and 1. Let's say these are our labels, class labels. Class 0 means some class and class 1 means some other class. That kind of problem is known as binary classification problem. In that case, one may come up with estimating, for example, what is the probability that yi is equal to 1 given xi, or maybe one need to predict what is the probability that yi is equal to 0 given xi. So these probabilities may be more plausible, or maybe if we just have only two classes, then we may define, let's say, the probability of yi being 0 given xi may be defined as 1 minus probability that yi is equal to 1 given xi. Either way, it is good to come up with a probabilistic measure rather than exact measure, how confident our model is in assigning a particular label out of these two labels. Although I'm discussing just in the two labels, but it can be extended to multiple labels, and more fancy version of it is called softmax. Anyways, right now we will stick to just two labels. So one way is to come up with this function as a following way. So fw, for example, xi might be 1 over 1 plus e raised to the power minus w transpose xi plus w naught. That horrible looking function is actually the following thing. So you have 1 over 1 plus e raised to the power minus, let me write this as minus, let's say this is z. And z here is actually minus w transpose xi. So w is the parameter vector, have the same number of coordinates as there are in xi, and this is the bias parameter w naught. So this z. Now obviously this x is a vector, w is a vector, that is a real number. That's one real number. Let's say r1. That's a real number. That's r2. And eventually if I add two real numbers and take a minus sign of that, that z eventually is a real number, maybe a positive number, negative number, maybe 0, whatever. So if z is really very big number, it's big positive number, then this e raised to the power minus big number will become very small, and 1 over, so let me highlight that, then this 1 over 1 plus very small number actually approaches to 1. So this function in that case will give values that are very high and close to 1, but will never exceed 1. On the other hand, if z is really small and a negative number, then 1 over 1 plus minus a negative number, very small number, will give this value to be very big, and the whole fraction squeezes to 0. So this particular function has a property that it has minimum value. Actually, the values are between 0 and 1. And the values that are very, very negative, if the z values are negative and in the magnitude they are big, the output is very close to 0. And on the other extreme, the output is very close to 1. And at 0, if z is exactly 0, the output is 0.5. So the whole goal is to come up with these w parameters. And this particular function, by the way, is known as logistic function. And it is also called sigmoid function, and it has very good implications in neural networks. So the goal is to come up with, so if we have this FW function in this way, then we can just threshold, for example, we can assign the value or the prediction value y hat I to be 1 if this value at xi is greater than 0.5. Otherwise, the prediction can be assigned to 0. So if we can learn these W's from the training data, then we can come up with these predictions by thresholding this particular value from maybe 0.5 or maybe a biased value, let's say 0.7 or 0.4 or something like that. So that's about logistic function. Next, we move towards cross entropy. One very straightforward way, for example, straightforward way is to come up with a loss function. For example, loss for ith example is to come up with the squared loss, yi hat, maybe this thing. It turns out that if yi is represented as the output of the logistic function, then the squared loss is no longer convex, it becomes non-convex. In simple terms, it is very difficult to optimize this loss function and to get the parameters w out. Another kind of loss function that is much more popular in that case, and the loss function is convex, is cross entropy. Here you can assume this p as y hat, and this p again is a y hat. And this loss function works like the following. If the true label is 1 and our prediction is 1, remember log of 1 is always 0, then the loss is 0. Minus log of minus 0 is eventually 0. But on the other hand, if the true label is 1 and our prediction is 0 or something very close to 0, then this minus log of very small value that is approaching to 0, that is a very big number, and that's a loss, and we have to minimize that loss. On the other hand, if our prediction y is equal to 0, if the actual prediction is 0 in this particular case, and we have predicted 0, then we are fine. But if the actual value is 0 and we have predicted 1, then we again are going to return a very big number, which is the loss. So the end goal is to minimize this particular loss, which is known as the cross entropy loss. And the hand-waving kind of argument in that without proof is that this cross entropy loss function is convex, which means we can find out the best W's iteratively or efficiently. Yeah. Next, once we have this cross entropy loss function with logistic function as our model, cross entropy loss function set, the next thing is how to come up with the parameters W 1 over 1 plus e raised to the power minus W transpose xi plus W naught. How to come up with these parameters that actually minimize our loss. So some set of parameters are these, and one additional parameter is this called bias. How to come up with these parameters that minimize our total loss. So loss for example 1 plus loss for example 2 plus loss for example 3, so on for loss for example n, for example, that's our training data. And let's say this is our average loss. This loss depends upon W and W naught. So how to come up with this W and W naught such that this total loss become as minimum as possible? It turns out this total loss is, it is difficult to find out W and W naught in a closed form way from this loss using cross entropy loss function, but a gradient descent algorithm, actually an iterative algorithm exists to do that. What you do is you start from any random W's, and you think that that is the best W at the time. Let's say this one. But then you compute the gradient of the loss, which tells you the best next direction to move in, and you take a step in that direction. And that taking a step in that direction guarantees that your new loss is better than or smaller than the previous one. Then at that new location, you again compute the gradient and you come up with a direction. You take a step, and iteratively you move until you do not have a very you do not have, for example, a room of improvement, or your total number of iterations exceed, or stuff like that. So that is known as gradient descent. By the way, if you want to understand gradient descent in more detail, please see the link below. We have another video on our YouTube channel just on gradient descent, and a lot of details in there. So in a nutshell, at the end of the day, we have logistic function, which is our prediction at any ith point. And this is written in this way: 1 over 1 plus e raised to the power minus w transpose xi plus w naught. And we also have for every, in the training data, for every data point or object, we also have its true label. And this is the label we are going to predict. So we really want to come up with the predicted label as close to the true label. So we want to minimize our loss. And we minimize our loss through gradient descent. And using, in all that scheme, using a logistic function for prediction makes the name as logistic regression. Let's do some hands-on in Python. So for example, let me give you a quick tour of logistic regression in Python. So from scikit-learn, we import a linear model, which is logistic regression, and we import that as LR. For train trace split, we use this thing. And for accuracy measurement, let's use the confusion matrix. And this is for display and for array management. So let's do that. And let me, for example, here load an iris data. That's the iris data. It has several, for example, fields. So that's the attribute 1, attribute 2, attribute 3, attribute 4. You can think that our x1 has 4 coordinates, and that's the class label, which is y1. In this particular case, we have the class labels we have are, for example, if I just show you np.unique, our class labels are Setosa, versicular, and Virginica. These are the 3 classes in this particular case. I have not told you how to extend the model we have seen so far. I have not told you how to extend that model for multiple classes, but here I'm using the scikit-learn model for multiple classes. Okay, next what we do is we drop that label attribute from the data set, so that we build a model. Now the species attribute is no longer there. Now we want to build a model that actually learns from data and try to predict. For that, we keep some of the data out so that we test performance on that data, and that is not used in the training part. So on the training portion of the data, we actually train a logistic regression model and fit our model on that. Next, on the unseen data, so far, we actually call our model and ask it to predict. Now these are all the predictions, Y predictions, and these are the actual corresponding labels. Let's see how better we have performed so far. So if you see, it's basically, in this particular case, you got only one error. All Setosas, they are labeled as Setosas, or versiculars, they are labeled as predicted as versiculars, except for one that is misclassified as Virginica. And all Virginicas, they are actually classified correctly. So that was a very quick tour of logistic regression, how you can implement logistic regression very easily. So I hope you have liked this video. We have a lot of other videos related to data science and artificial intelligence. Please go through the links below and join us. Do subscribe our channel, like this video, and share this with your friends. Hope to see you next time.